अच्छे ही होंगे। तो आज सॉल्यूशन का चैप्टर आपको एनिमेशन के थ्रू समझा देते हैं और फिर नेक्स्ट डे बाय लेक्चर, नेक्स्ट वीडियो में बाय लेक्चर आपको समझाएंगे। और सॉल्यूशन के चैप्टर को एक बार थोरोली देखिए, जो नोट्स हैं उनको बनाने की कोशिश कीजिए और उसको समझिए। सॉल्यूशन कंप्लीट आपको मैं चैप्टर दे रहा हूँ, जिसमें कि बेसिक से लेकर के और राउल्ट लॉ से लेकर के और जो आपके न्यूमेरिकल्स हैं उन सब के स्टेप बाय स्टेप आपको सबके वीडियोस, सबके टॉपिक्स आपको इस वीडियो में मिल जाएंगे। लेकिन आपको पेशेंसली देखना, क्योंकि जब एलाबरेट करके टॉपिक्स में बनाने की कोशिश करता हूँ तो वहाँ पे थोड़ा लॉन्ग वीडियो तो हो जाता है। अब फिर खाना पूर्ति करने का काम फिर होता नहीं, वो संभव नहीं हो पाता। तो थोड़ा सा लॉन्ग वीडियो है, लेकिन आप पेशेंसली इसको देखें, पेशेंसली समझें, और फिर जब मैं इसी चैप्टर को लेक्चर से समझाऊंगा तो फिर आप उसको भी समझें। तो ये डबल इसलिए मैं करने की कोशिश करता हूँ कि आपको एकदम अच्छे से थोरोली बातें समझ में आए, क्योंकि मैं बार बार कहता हूँ कि अब जो बोर्ड के एग्जाम है वो सिर्फ ये थ्योरेटिकली नहीं है, ऑब्जेक्टिव क्वेश्चन पे ज़्यादा जोर दिया जा रहा है, यानी कि कंसेप्ट आपका क्लियर होना चाहिए। तो उन कंसेप्ट को क्लियर आप तभी कर सकते हैं जब आप उसको थोरोली पढ़ें। ओके, तो आते हैं वीडियो पे। और एक रिक्वेस्ट है आप लोगों से कि अगर आपको अच्छा लगता है तो आप इसको प्रेफर करें, दोस्तों को शेयर करें और लाइक, कमेंट, ये वो जो भी होते हैं ताम झाम की चीज़ें, तो वो करें, है ना। तो चलते हैं अपने वीडियो पे और देखते हैं कि आखिर आज क्या देखना है सौरभ से।
Introduction. What are you doing, son? Father, I'm just reading my favorite comic. Ajay, don't use tap water for drinking purpose. It may be contaminated. Always use RO purifier's water for drinking purpose. Okay, father. Father, I want to ask you something about this. How does RO purify work? Okay, son. I will tell you. It works on the principle of reverse osmosis. The tap water is a solution of water, minerals, metals, or some impurities. RO purifier has a semi-permeable membrane, which allows only water molecules to pass through it, and other molecules cannot pass through the semi-permeable membrane. The tap water acts as a solution, and pure water acts as a solvent. The membrane allows only solvent molecules to pass through it. Okay, father. Now I get the answer of my question. And I want to know more about this. Son, to know more about this, you have to study about solutions. Students, today we will study more about solutions. Objectives. At the end of this lesson, you will be able to define vapor pressure, explain Raoult's law, describe Raoult's law for solution of two volatile liquids, differentiate ideal and non-ideal solutions, understand positive and negative deviation, know colligative properties, define osmosis and reverse osmosis, understand abnormal molar masses, and calculate Van Hoff's factor. Vapor pressure of liquid. The pressure exerted by the vapors above the liquid surface in equilibrium with the liquid at a given temperature is called vapor pressure of the liquid. The vapor pressure of a liquid depends on nature of liquid and temperature. Nature of liquid. Liquids which have weak intermolecular forces are volatile and have greater vapor pressure. For example, dimethyl ether has greater vapor pressure than ethyl alcohol. Temperature. Vapor pressure increases with increase in temperature. This is due to the reason that with increase in temperature, more molecules of the liquid can go into vapor phase. The variation of vapor pressure of a liquid with temperature is given by Clausius equation. Here, P1 and P2 are vapor pressures at temperature T1 and T2 respectively, and R is the universal gas constant. Vapor pressure of the solution. When we add a small amount of non-volatile solute to the solvent to form a solution, then the vapor pressure of the solution is only due to solvent. In that case, vapor pressure of the solution is less than that of the pure solvent. In the case of solution, a part of the liquid surface is occupied by solute particles, which are non-volatile. Therefore, evaporation of the liquid will take place from a lesser surface area. This results in lowering of vapor pressure. Raoult's law. The vapor pressure of a solution containing non-volatile solute is directly proportional to the mole fraction of the solvent. In case of solution containing two components, volatile solvent and non-volatile solute, the vapor pressure of solution is given as PA is equal to K into XA, where K is proportionality constant. For pure liquid, XA is equal to 1. In this case, K becomes equal to vapor pressure of the pure solvent, which is denoted by P, not A. Thus, PA is equal to P naught A into XA. For solutions obeying Raoult's law at all concentrations, its vapor pressure would vary linearly from 0 to the vapor pressure of pure solvent. Raoult's law for solution of two volatile liquids. When two volatile liquids A and B are mixed to form a solution, the vapor phase consists of vapor of both the components of the solution. The partial vapor pressure of each of the component depends on the mole fraction of corresponding component. PA is equal to PA naught into XA, and PB is equal to PB naught into XB. This relationship is called Raoult's law. It states that for a solution of two or more miscible volatile liquids, the partial vapor pressure of each component of the solution at a given temperature is directly proportional to its mole fraction. According to Raoult's law, a plot of PA against XA should give a straight line passing through PA naught when XA is equal to 1. Similarly, a plot of PB against XB is a straight line passing through PB naught when XB is equal to 1. The total vapor pressure P exerted by the vapor above the solution is the sum of PA and PB. P is equal to PA plus PB. By putting XA is equal to 1 minus XB, we get the relation P is equal to bracket PB naught minus PA naught bracket close multiplied by xb plus Pa naught. Similarly, by putting xb is equal to 1 minus xa, we get the relation P is equal to Pa naught minus Pb naught whole multiplied by xa plus Pb naught. Since Pb naught and Pa naught are constant at given temperature, therefore, the total pressure P is a linear function of xb or xa. Ideal solutions. A solution is called an ideal solution if it obeys Raoult's law over a wide range of concentration and at specified temperature. For an ideal solution, P is equal to Pa plus Pb. It can be written as P is equal to Pa naught into Xa plus Pb naught into Xb. Liquids having similar nature and structure are likely to form ideal solutions. For example, mixture of methanol and ethanol. Reasons for formation of ideal solutions. A solution of two miscible liquids A and B will be ideal if two essential conditions are fulfilled. If the force of attraction between molecules of A and B is equal to the force of attraction within molecules of A and force of attraction within molecules of B. The solution of A and B liquids will be ideal if A and B have similar structures and polarity. Example on ideal solution. Let's take an example of ideal solutions. Benzene and toluene form a very nearly ideal solution. At 313 Kelvin, the vapor pressure of pure benzene and toluene are 160 mm Hg and 60 mm Hg respectively. Assuming an ideal solution behavior, calculate partial pressure of benzene and toluene and total vapor pressure of the solution made by mixing 4 mole of toluene and 1 mole of benzene. Let's see the solution. We know that mole fraction of benzene is equal to moles of benzene upon moles of benzene plus moles of toluene whole. On calculating, we get mole fraction of benzene is equal to 0.2 and mole fraction of toluene is 0.8. Now, we calculate the partial pressure and we get partial pressure of benzene is equal to 32 mm of mercury. Similarly, partial pressure of toluene is equal to 48 mm of mercury. Hence, total vapor pressure of solution is equal to 80 mm of mercury. Non-ideal solutions. A solution which does not obey Raoult's law for all concentrations is called a non-ideal solution. Essential conditions for a non-ideal solution are: total volume of the solution should not be equal to volume of solvent A plus volume of solute B. Molecular interaction between the molecules of A, molecules of B, and molecules of A and B are of different magnitude. Therefore, change in enthalpy on mixing A and B will not be zero. Raoult's law is not obeyed. A non-ideal solution can show either positive or negative deviation from Raoult's law. Positive deviation. The deviation will be called positive when the partial pressure of each component and the resultant total pressure are greater than the pressure expected on the basis of Raoult's law. For example, the solution of water ethanol and benzene acetone shows positive deviation. The intermolecular forces between solvent-solute molecules are weaker than those between solvent-solvent and solute-solute molecules. This shows that the vapor pressure of the solution will be higher.
Negative deviation. The deviation is called negative deviation if the partial pressure of each component and resultant total vapor pressure are less than the pressure expected on the basis of Raoult's law. For example, the solution of water nitric acid and chloroform acetone shows negative deviation. The intermolecular forces between solvent-solute molecules are stronger than those between solvent-solvent and solute-solute molecules. This shows that the vapor pressure of the solution will be lower. Colligative properties. Those properties of dilute solutions containing a non-volatile solute dissolved in a known amount of a solvent, which depend upon the number of solute particles and not upon their nature, are called colligative properties. The colligative properties of dilute solutions are used to determine the molecular mass of the dissolved substance. The various colligative properties are lowering in vapor pressure, elevation in boiling point, depression in freezing point, and osmotic pressure. Relative lowering in vapor pressure. The addition of a non-volatile solute to a volatile solvent decreases the escaping tendency of the solvent molecules from the surface of solutions, as some of the surface area is occupied by non-volatile solute particles. According to Raoult's law, the relative lowering of vapor pressure is equal to mole fraction of solute. Thus, Pa naught minus P upon Pa naught is equal to Xb, which is equal to Nb upon Na plus Nb. For a dilute solution, Na is much greater than Nb. Hence, neglecting Nb in the denominator, we have Mb is equal to Pa naught upon Pa naught minus P multiplied by Wb into Ma upon Wa. Elevation in boiling point. Boiling point is the temperature at which the vapor pressure of a liquid becomes equal to the atmospheric pressure. When a non-volatile solute is added to a volatile solvent, the vapor pressure of the solvent decreases. In order to make this solution boil, its vapor pressure must be increased by raising the temperature above the boiling point of the pure solvent. The difference in the boiling point of solution and that of pure solvent is called elevation of boiling point. Elevation of boiling point is denoted by delta Tb, which is equal to Tb minus Tb naught. For dilute solution, the elevation of boiling point is directly proportional to the molar concentration of the solute in the solution. Kb is called molar elevation constant. Molar elevation constant is defined as the elevation in boiling point when 1 mole of a non-volatile solute is dissolved in 1 kilogram of solvent. Depression in freezing point. Freezing point is defined as the temperature at which the vapor pressure of a substance in its liquid phase is equal to its vapor pressure in the solid phase. A solution freezes when its vapor pressure equals the vapor pressure of the pure solid solvent. When a non-volatile solute is added to the solvent, its vapor pressure in the solution decreases. The difference in the freezing point of pure solvent and that of the solution is known as depression in freezing point. Depression in freezing point is denoted by delta Tf, which is equal to Tf naught minus Tf. For dilute solution, depression in freezing is directly proportional to molality of the solution. Kf is called molar depression constant. Molar depression constant is defined as the depression in freezing point when 1 mole of non-volatile solute is dissolved in 1 kilogram of solvent. Osmosis. The passage of solvent from pure solvent or from solution of lower concentration into solution of higher concentration through a semi-permeable membrane is called osmosis. This movement of solvent is only in one direction. Semi-permeable membrane. A membrane through which only solvent molecules can pass, but not the solute ones. For example, cellophane, parchment paper, and wall of living cell. Osmotic pressure. Osmotic pressure is defined as the excess hydrostatic pressure that builds up when the solution is separated from the solvent by a semi-permeable membrane. It is denoted by pi. Osmotic pressure is proportional to molarity of the solution at a given temperature. Pi is equal to CRT. Put the value of C in the equation. We get pi is equal to WB into R into T divided by MB into V. We calculate the value of MB as WB into R into T divided by pi into V. Reverse osmosis. If a pressure larger than the osmotic pressure is applied to the solution side, the pure solvent flows out of the solution through the semi-permeable membrane. In this way, the direction of osmosis is reversed, and so the process is called reverse osmosis. Reverse osmosis is just opposite to the process of osmosis when an extra pressure is applied. Reverse osmosis is used in desalination to get pure water from seawater. Abnormal molar masses. Association. Association of molecules leads to decrease in the number of particles in the solution. Results a decrease in the value of colligative property. As colligative property is inversely related to the molecular mass, therefore, higher value is obtained for molecular mass than normal values. Dissociation. Dissociation leads to increase in the number of solute particles in the solution. Results increase in the value of colligative property. Since colligative property is inversely related to the molecular mass, therefore, molecular mass of such a substance as calculated from colligative property will be less than its normal value. Van 't Hoff's factor. It is defined as the ratio of normal molecular mass to the observed molecular mass of the solute. It is denoted by I. I is equal to normal molecular mass divided by observed molecular mass, or I is equal to observed colligative property divided by calculated value of colligative property. Van 't Hoff's factor expresses the extent of association or dissociation of the solute particles in the solutions. In case of association, I is less than 1. In case of dissociation, I is greater than 1. Neither association nor dissociation, I is equal to 1. Did you know? If a saturated solution is heated, the liquid expands, making room for more solute to dissolve. If a saturated solution cools or is left to evaporate, there is less room for solute, so the solute is precipitated. Precipitated solute molecules often linked together to form solid crystals. Osmosis is vital to many body processes, including the workings of the kidney and the nerves. Summary. Let us summarize what we have learnt. The pressure exerted by the vapors above the liquid surface in equilibrium with the liquid at a given temperature is called vapor pressure of the liquid. When we add a small amount of non-volatile solute to the solvent to form a solution, then the vapor pressure of the solution decreases. The vapor pressure of a solution containing non-volatile solute is directly proportional to the mole fraction of the solvent. For a solution of two miscible volatile liquids, the partial vapor pressure of each component of the solution is directly proportional to its mole fraction. Liquids having similar nature and structure are likely to form ideal solutions. Boiling point is the temperature at which the vapor pressure of a liquid becomes equal to the atmospheric pressure. Osmotic pressure is the excess hydrostatic pressure that builds up when the solution is separated from the solvent by a semi-permeable membrane. Van 't Hoff's factor is defined as the ratio of normal molecular mass to the observed molecular mass of the solute.
Introduction. Today, Rohan and Aryan are sitting in a cafeteria and enjoying some stuff. Aryan, may I ask you something? Yeah, sure. When you open the cap of the bottle, the bubbles are coming out continuously. Why? Okay, I will tell you. When the bottle is closed, the gas in the bottle is under pressure and remains dissolved. But when the bottle is opened, the pressure is removed and the dissolved gas leaves the liquid rapidly in the form of bubbles. This is an example of Henry's law of solubility of a gas. Okay, now I get the point. But I want to know something more about this. Rohan, to know more, you have to explore about the solutions. Students, you must be curious to know more about this. Today, we will discuss more about the solutions. Objectives. At the end of this lesson, you will be able to define solutions, explain components of binary solution, know about types of solutions, express concentration of solutions, calculate normality, molarity and molality, calculate mole fraction, understand solubility, analyze solid-liquid solutions, analyze gas-liquid solutions, define Henry's law, know about applications of Henry's law. Definition. A solution is a homogeneous mixture of two or more pure substances, whose composition may be altered within certain limits. The solution may be homogeneous in nature, but it retains the properties of its constituents. The substances which make up the solution are generally called its components. The solution of two components is referred to as binary solution. Components of binary solution. The two components of the solution are solvent and solute. Solvent. It is that component of the solution which is present in a relatively large proportion in the solution and whose physical state is same as that of the resulting solution. Solute. It is the second component of a binary solution, which is present in relatively small proportion. Types of solutions. In a binary solution, components can be either solid, liquid, or gas. There are three types of solutions: gaseous solutions, liquid solutions, and solid solutions. In gaseous solutions, gas is the solvent. They are categorized as follows: solid in gas, for example, camphor vapor in nitrogen gas. Liquid in gas, for example, water vapors in air. Gas in gas, for example, mixture of gases or air. In liquid solutions, liquid is the solvent. They are categorized as follows: solid in liquid, for example, salt in water or sucrose in water. Liquid in liquid, for example, mixture of miscible liquids. Gas in liquid, for example, aerated drinks. In solid solutions, solid is the solvent. They are categorized as follows: solid in solid, for example, alloys. Liquid in solid, for example, mercury in zinc. Gas in solid, for example, adsorption of gases on metals. Expressing concentration of solutions. The concentration of a solution refers to the amount of solute present in the given quantity of solution or solvent. Mass percentage. It is defined as the number of parts by mass of solute per 100 parts by mass of solution. If Wb be the mass of solute B and Wa be the mass of solvent A, then mass percentage of B is equal to Wb upon bracket Wa plus Wb bracket close multiplied by 100. Volume percentage. It is defined as the number of parts by volume of solute per 100 parts by volume of solution. If Va and Vb be the volumes of component A and B, then volume percentage of B is equal to Vb upon bracket Va plus Vb bracket close multiplied by 100. Normality. Normality. It is defined as the number of gram equivalents of the solute present in 1 liter of the solution or milli-equivalents of solute present in 1 milliliter of solution. It is represented by N. Mathematically, normality is represented by N is equal to Wb in grams divided by product of gram equivalent mass of B and volume of solution in liter. A solution having normality equal to 1 is called a normal solution. Molarity and molality. Molarity. It is defined as the number of gram mole of the solute present in 1 liter of solution or millimole of solute present in 1 ml of solution. It is represented by M. Mathematically, molarity is represented by M is equal to Wb in grams divided by product of gram mole mass of B and volume of solution in liter. A solution having molarity 1 is called molar solution. Molality. It is defined as the number of gram-mole of the solute present in 1000 gram of the solvent. It is represented by small m. Mathematically, molality is represented by small m is equal to Wb in grams divided by product of gram-mole mass of B and Wa in kilogram. A solution containing 1 mole of solute per 1000 gram of solvent has molality equal to 1 and is called a molar solution. Mole fraction. Mole fraction is defined as the ratio of number of moles of one component to the total number of moles of all the components present in the solution. It is denoted by X. Let us consider a solution that contains the components A and B. WAG of A and WBG of B are present in it. Number of moles of A is given by WA upon MA. Number of moles of B is given by WB upon MB. Total number of moles of A and B is equal to NA plus NB. Mole fraction of A is given by NA divided by Na plus Nb. Mole fraction of B is given by Nb divided by Na plus Nb. By adding mole fraction of A and B, we get Xa plus Xb is equal to 1. It implies that the sum of mole fractions of all the components in a solution is always unity. Example on mole fraction. Let's take an example of mole fraction. 1 deciliter solution of NaOH contains 4 gram NaOH. Calculate mole fraction of NaOH in the solution. Let's see the solution. We know that 1 deciliter solution is equal to 100 cubic centimeter of solution. Mass of 100 cubic centimeter of solution is equal to 100 into 1.0398, which is equal to 103.8 grams. Mass of NaOH is equal to 4 gram. Mass of solvent, which is water, is equal to 103.8 minus 4, which is equal to 99.8 grams. Number of moles of NaOH, bracket N2, is equal to 4 upon 40, which is 0.10. Number of moles of water N1 is equal to 99.8 divided by 18, which is equal to 5.54. Mole fraction of NaOH, N2, is equal to N2 upon N1 plus N2 whole, which is equal to 0.018. Hence, mole fraction of NaOH in the solution is 0.018. Formality and parts per million. Formality. It is defined as the number of gram formula masses of the ionic solute present in 1 liter of the solution. It is represented by F. Mathematically, formality is represented by F is equal to Wb in grams divided by product of gram formal mass of B and volume of solution in liter. A solution containing 1 gram formula mass of solute per liter of the solution has formality equal to 1 and is called formal solution. Parts per million. It is defined as the number of parts by mass of solute per million parts by mass of the solution. It is abbreviated as ppm. Mathematically, ppm is represented by ppm is equal to Wb divided by Wa plus Wb into 10 raised to the power 6. Solubility. Solubility of a substance is its maximum amount that can be dissolved in a specific amount of solvent. It depends upon the nature of solute and solvent, as well as temperature and pressure. The extent of the solubility of a substance in a specific solvent is measured as the saturation concentration, where adding more solute does not increase the concentration of the solution. We consider the effect of these factors in solution of a solid or a gas in a liquid. Solid-liquid solutions. A small amount of solute is dissolved in a large quantity of solvent. Dilute solution. If the amount of solvent is large excess as compared to the solute, the solution is referred to as a dilute solution. Saturated solution. A solution is said to be saturated if it holds the maximum amount of the solute at a given temperature in a given quantity of the solution. Solubility. It is defined as the maximum amount of solute that can be dissolved in a 100-gram solvent at a given specified temperature. The solubility of solid into liquid depends upon the nature of solute, nature of solvent, and temperature. Causes of solubility of solid in a liquid. Many types of forces of attraction are operated when a solute is mixed with a solvent. Inter-ionic attraction in the solute molecules. Ions are held together in the lattice due to electrostatic forces. Due to these forces, molecules are stabilized and the energy released is called lattice energy. Intermolecular attraction between solvent molecules. Water is a polar solvent because of the electronegativity difference between hydrogen and oxygen atoms, constituting water molecule. A dipole is thus created, giving rise to dipole-dipole attraction between water molecules. Effects of hydration energy and temperature. Hydration energy. It is defined as the energy which represents forces of attraction between solute and solvent molecules. If hydration energy is greater than lattice energy, then solution is easily formed. Temperature. Saturated solution represents equilibrium between undissolved solute and dissolved solute. If delta H of solution is negative, then the dissolution is exothermic. In this case, as the temperature increases, solubility decreases. If delta H of solution is positive, then the dissolution is endothermic. In this case, as the temperature increases, solubility increases. Gas-liquid solutions. Gases are generally soluble in water and in other solvents to a limited extent. Solubility of gas in liquid solutions depends on the following factors. Nature of gas. Easily liquefiable gases are generally more soluble in common solvents. Nature of liquid. Those gases which easily form ions in solution are more soluble in water than in other solvents. Temperature. With rise in temperature, the solubility generally decreases because gas is expelled, but some gases find their solubility increased at a higher temperature. Pressure. Pressure is an important factor affecting the solubility of gas in liquids. This is governed by Henry's law. Henry's law. Henry's law states that at a constant temperature, the solubility of a gas in a liquid is directly proportional to the pressure of the gas. Henry's law can also be stated as the partial pressure of a gas in vapor phase is proportional to the mole fraction of the gas in the solution. P is equal to kHx, where kH is the Henry's law constant and x is the mole fraction of the gas. Limitations. The pressure of the gas is not too high and temperature is not too low. The gas should not undergo any chemical change. The gas should not undergo association or dissociation in the solution. Applications of Henry's law. To increase the solubility of CO2 in soda water and soft drinks, the bottle is sealed under high pressure. The tanks used by scuba divers are filled with air diluted with helium to avoid the toxic effects of high concentration of nitrogen in the blood. At high altitudes, low blood oxygen causes climbers to become weak and make them unable to think clearly. Did you know? If a saturated solution is heated, the liquid expands, making room for more solute to dissolve. If a saturated solution cools or is left to evaporate, there is less room for solute, so the solute is precipitated. Precipitated solute molecules often link together to form solid crystals. Tap water is rarely pure water. It usually contains invisible traces of other substances. This makes water a solution. Summary. Let us summarize what we have learnt. A solution is a homogeneous mixture of two or more pure substances whose composition may be altered within certain limits. The concentration of a solution is the amount of solute present in the given quantity of solution or solvent. Normality is defined as the number of gram equivalents of the solute present in 1 liter of solution. Mole fraction is the ratio of number of moles of one component to the total number of moles of all the components present in the solution. Solubility of a substance is its maximum amount that can be dissolved in a specified amount of solvent. If the amount of solvent is large excess as compared to the solute, the solution is known as a dilute solution. gases which easily form ions in solution are more soluble in water than in other solvents. Henry's law states that at a constant temperature, the solubility of a gas in a liquid is directly proportional to the pressure of the gas.